This is the video for uptime routines. Here on the left we have the beginning of the routine, and on the right we have the end of the routine. I'm going to start on the left. Here, the first thing it says is it does a reset. That resets all probability distributions, and down here we're going to do a PEC instruction, and we want that to be set at the beginning of its seed. Then we set S to the game number. We set equally likely 21. That's going to be used down here when we do our PEC instruction. Then we set start to 1, and we divide it by 100. So it's going to be 0.01. Then we fill the 49 values at matrix with 0. Well, that's 7 times 7. We have a 7 by 7 matrix down here for our transition matrix. Then we set matrix plus 1 to start. Remember, that was figured out here to be 0.01. Well, at matrix plus 1 is this value here, and it is 0.01. Then it says for I of 2, down here to next I6 one at a time, it first wants to get a random value equally likely, and that equally likely value is 21. So it's going to give the probability of 0 through 20 equally likely. So each time it's going to be a value 0 to 20, but here is the seed it's to use. 1 plus S, where S is the game number. So that's the seed where it starts at. That means every time the game number changes, it's going to change the distribution it's using to pick the random values. In this case, if the game is number 1, the seed is 1. Game is 0, the seed will be 1. Once it gets that value that is going to be from 0 to 20, it adds 60 to it. Well, now it's going to be a value of 60 to 80. Then it divides it by 100. Well, now we know it's from 0.6 to 0.8. It's a fraction. The next thing it does, it then takes that fraction and multiplies it times the start value we had, which was 0.01, the first one, and then it says put in matrix plus I, this new value. Well, I started at 2, so it's this one. So this one here is 0.01 times that random value. And we see as it goes around here, I is going to change. It's going to be the next one with a random fraction times it, and another one, and another one, and another one, until it gets this very last one. Notice they keep going down in value because the fraction is always from 0.6 to 0.8 in value. So that's how these values are determined. All right? That's the end of that loop, so now we're over here. And it says set J to 7. And then for I of 1, and here we see next I6 one at a time. We're going to set matrix plus J to a 1. Well, J starts at 7. Well, that's this value here, offset 7. And here we see it was set to a 1. But now, the next line says add 8 to J. Well, if we added 7 to J, it would just come down 1. But it's also going over 1. It's adding 8. So along this line going down here, it keeps putting 1s. So when that is finished, it does that 6 times, and you'll see there's 6 1s here. The one that doesn't have a 1 is the first row. The others of the 7 have a 1. The next thing after it does those 1s, it says sum the values, the 7 values it says in matrix. Well, that's the first 7 values. But remember, this started out being all zeros. So at the time it's summing them up, this first one is 0. It could have said add the 6 values starting at matrix plus 1 here. But he said might as well add the first one too. We'll start at matrix. So it adds those 6 values up that we already made, puts the value in t. Then it sets the value at the first position to 1. And then guess what? It subtracts the t from the matrix value. Alright, so then that is the difference of the sum of all these from 1. Hey, therefore this first row adds up to 1. We notice all the other rows add up to 1. This is a transition matrix. It's going to be used for a Markov chain. Alright, so once we figured out what that value is, then it says set LS to 7. Well, that's the offset to get between the rows, and, well, there's 7 values in a row. The offset is 7. So we set NS, though, to 1007, indicating that it's a square matrix 7 by 7. The action down here, multiply list, needs to know both of these values. Well, the next thing it does, it says for I of 1, next I8, go around here, and what it's going to do, it's going to keep multiplying steady state times whole matrix down here, but first it moves the 49 values from steady state to whole matrix, and then multiplies it times itself, and every time it goes around again, it does the same thing. So it's the second power, the fourth power, the eighth power, and so on, till it gets to the 256 power of the matrix. And down here is where the 256 power of the matrix is. And we said in the game that we wanted to have a 0.93 probability that the machine was running. All these probabilities over here was that the machine broke down. The 0.01 said the machine broke down and went into this row, number 1, which the probability the next time was it would be back to working again. And here at the very end, we had a very small probability that it would go all the way down to the last row, which means then it has to go to this row, then to this row, then to this row, and so forth and so forth and so forth, till a machine finally gets working again. So for every one of these probabilities, there's a different amount of time that the machine will be down. It has to get back to working again. We found out down here, it's a 0.934738 probability that the machine is working. If what we wanted to know that it was better than a 93% working, it is. So we would accept this criteria and keep the machine running the way it is. Alright, this is the end of the video on uptime routines.